Thank you so much, Professor Deng. It's really impressive, the variety of projects and contributions that you have. And by the way, SMU University in Singapore is one of the several universities that in our collaboration research program with Singapore and Tel Aviv University, we have running researches at the moment. So I would like to present our fourth speaker. He is a speaker, a returning speaker that the committee of this conference have decided that we cannot talk about beyond IT and not ask him to join us even for a short session to give his view. I'm talking about Professor Yuval Elovici, the director of the Deutsche Telekom Innovation Labs at Ben-Gurion University in Israel. He is the head of the BGU Cyber Security Research Center and research director of the iTrust of SUTD in Singapore. Professor Elovici, please.
Thank you. Let's try to connect it. אני בחוץ? מה? רגע. לא רואה כלום. Okay. Great. I'm surprised that it's working. Okay, I chose with Yaniv to talk about something that is a little bit interdisciplinary and relatively very, very disruptive. We started to work 3 years ago in a new field called how to secure additive manufacturing. First of all, I want to convince you about the challenge, and later on to show you several mitigation technologies that we are currently developing. This work is mainly being done by Sofia, my PhD student. First of all, what is additive manufacturing? Everybody knows about additive manufacturing. We talk about 3D printers. 3D printers are actually taking material and by adding the material are generating new objects. Now the process of generating such objects is very, very complex, but what's the motivation? How it relates to cybersecurity? In the last years, it was approved also to 3D print critical components that are being used, for example, by the aviation industry. So if cyber attackers will be able to intervene in the process of creating 3D objects, they will be able to insert a void that eventually may create a critical infrastructure to collapse. For example, an aeroplane. And I will show you a demonstration in a few seconds how we demonstrated such an attack. So first of all, what is the process that involves additive manufacturing? Usually, some mechanical engineer is taking a CAD tool and is designing a new type of object. Then the object is converted to G-code. G-code are instructions to a specific 3D printers that's supposed to take the instructions and to convert them into a printed object. Now, when we analyze the additive manufacturing workflows, there are many opportunities for attackers. For example, the attacker may attack the computer of the designer. The attacker may attack the 3D printer itself. So there are multiple opportunities how to damage and to create a situation in which the printed component includes such a defect that may influence the operation of the system that is going to use it in the future. So we did a very, very detailed systematic analysis of how attackers may interfere in an additive manufacturing process. So for example, first of all, we identified the attack vectors, the software, the hardware. What are the compromised elements that may be attacked by the attacker? It could be the controller PC, it could be the network, it could be the printer itself. What is the influenced elements? The files that I want to print, or the code that I'm going to send to the printer, and so on. What are the potential influences that I may influence the process itself? And what is the attack target? So maybe what I described to you is not clear, and we realized that in our community, the understanding of the impact was not clear. So we decided, like good researchers, to do a POC and to demonstrate what attackers may do if they were going to influence in a bad manner the additive manufacturing process. So we decided, from the point of view of the attack vector, to use a very, very simple phishing attack. What we are going to attack? We are going to attack the controller, PC. Then we are going to modify the target element, the influence elements, is the file that the user wants to print in order to create a critical component. What is the defect that we want to do? Is to insert gaps, as I'm going to illustrate in a few seconds. And then the real impact is going to be on the object that is going to use the printed component. So what we decided to do is to attack a design of a blade. This is the blade of a drone, DJI drone. By the way, we couldn't find the design file of this propeller, so we actually 3D printed it to obtain a fake propeller that actually works, that we managed to print it and it's really working. Then we added a defect. We added here, in this joint, a gap of 0.1 millimeter gap that is very, very difficult to identify it. But in order for the propeller not to break immediately, we added 2 pins here that actually connects very, very weakly this part of the blade to the main part of the propeller. So maybe if it's not clear, I will show you a very, very short video that illustrates the entire attack. So what you see here, first of all, we are doing a very, very simple phishing attack against the users that's supposed actually to print the blade in order to be used on its drone. So in this case, back then, 1 year ago, we used a 0-day vulnerability in WinZip to demonstrate the attack. So we sent the victim a very, very simple email. And the only goal is to gain access to the computer of the user that's supposed to print the object itself. So this is the CNC of the attacker. We are going to gain access to the controller PC of the user. Once we get the access, what we are going to do is we are going to look for the design file of the propeller. So here we enter to the compromised computer. It could be done in a variety of ways, doesn't matter how. Now we looked, we found the design of the DJI propeller. The attacker is downloading the design file. And then what the attacker is doing is actually trying to improve this design by adding some kind of a void. So you see, this is how we did it. We added the void here, the connection. We added the gap and then added a connection to weakly connect the propeller to the main part. And we uploaded back to the user the improved version of the blade. So now the victim is coming in the morning. It wants to print the new object. And this is what it looks. It sees nothing. It prepares the blade for the printing. This is the preparation phase to generate the G-code. This is the printing phase. As you see, the victim will see nothing when he prints the object. These are 2 samples. And later on, we tested to see how it works. So we designed the defect in a way that exactly after 1 minute and 40 seconds, the blade will break. It's a fatigue attack against the blade. What you see that happens later on, it flies, and after 2 minutes, one of the blades that we attacked breaks, and actually that cyber attack was not against the blade, it was against the drone itself, because the drone broke, and these are the 2 segments of components. So what we did actually in this first part of our research that was accepted yesterday to Woot is just to demonstrate the process of attacking an additive manufacturing process. What we are currently working is in trying to automate the process in a way that we don't need to download the file and to compromise it. We want to write a malware that is going to look for STL files, design files, would look for the to the weak spots, and it's going to add the voids completely automatically. We believe that it can be done. Currently, we are working on it. But what about mitigation? So we also have working on very hardly on mitigation techniques. Since I'm very, very limited in time, I will tell you what we actually managed to accomplish. Since usually when cyber attackers are attacking a specific network, we assume that they can compromise every part of this network. So we looked for an out-of-band solution that will verify that whatever we are printing is exactly like the designer designed it. So what actually we did? We developed a new method, we call it audio fingerprint, that actually we are taking a mobile phone, we place the mobile phone close to the printer, and we are listening to the printing process. At least the 3D printer that we are using, I have at least 3 motors, they are generating a lot of noise. So we are listening to the printing process, and we generated a signature, an audio signature to the specific printed object under the assumption that there is no cyber attack. So this is like the audio fingerprint reference model. And later on, during the detection phase, what we are doing, we are actually placing a mobile phone and we are just listening to the printing of the object. And if there is a slight deviation, we immediately instruct the user to stop the printing because actually somebody managed somehow to do a cyber attack. It could be on the design file, it could be on the firmware of the printer, and whatever you are going to get is not exactly what the original designer planned. This signature is very, very complex. We took a window, we did an FFT, fast Fourier transform. Later on, we used the PCA to find the most important frequencies, and then we created a signature for a moving window along the printed object. So the idea that once you are downloading, for example, from the web, an object, and there is a risk that somebody modified it, you are going to download also the audio fingerprint, and you are going to compare when you are printing the two of them to verify that actually nobody managed to do a cyber attack and make you print something that eventually is going to fail when it's going to be embedded inside the real system. And we did a very nice evaluation for this approach, and it works very, very good. And we can detect any deviation of less than 1 second on the printed object. Just to illustrate with another short video how the process looks like. So you see it here, you see the mobile phone on the left, listening to what is being printed, and actually the mobile phone is going to warn us if actually there is a cyber attack that creates the printer to print something a little bit different than what we actually designed. Currently, we are working also on different mechanisms of how to guarantee that whatever is printed is accurate. I hope that I met your expectation, Yaniv, for the time. So thank you very, very much.